Hi there and welcome to this first video in a series of tutorials about Mitsuba 3, which is a differentiable renderer developed at EPFL in Switzerland. My name is Wenzel Jakob, and in this video I'll explain what Mitsuba is and when you might want to use it. A renderer takes a 3D scene as input and turns it into a realistic image. But in many cases the opposite direction is much more interesting. We want to start with images and find a 3D scene that is consistent with them. Mitsuba 3 can be used to go in both of these directions. Suppose we wanted to reconstruct the 3D shape and materials of this chair from images. In Mitsuba we would typically start with a crude initial guess, for example a sphere. If we now run the renderer, it will happily produce an image of the sphere, but that of course doesn't look anything like the chair. What is special about a differentiable renderer is that it can quantify that difference and reduce it by modifying the scene. Repeating that process over and over again using a technique called backpropagation eventually produces a reconstruction. This can be done for volumes, surfaces, and indirect effects, for example to compute a surface that will refract light into a particular pattern. My lab's research in the last 2 years has gone into making this process much more scalable and to address limitations of our previous generation system Mitsuba 2. There are a few other differentiable renderers out there, including TensorFlow Graphics, PyTorch 3D, and NVDiff-Rast. They're all based on rasterization, whereas Mitsuba uses ray tracing. That allows it to account for interreflection, shadowing, and other important physical effects. Differentiable rendering has superficial similarities to neural networks, which are also trained using backpropagation. The main difference is that neural nets are a black box representation. Training them produces opaque coefficients that are coupled to the training task. A differentiable renderer replaces the network with a computation that is based on physical laws. This means that every reconstructed parameter has a well-defined meaning and physical units. The results aren't tied to Mitsuba and can be processed by many other tools. Using Mitsuba requires some familiarity with the Python programming language. It can be used for rendering and inverse rendering problems in graphics and computer vision, but we think that the target audience is much larger. For example, there are many scientific disciplines where people spend lots of time analyzing images to infer the physical process that caused them to look the way they do. Differentiable rendering offers a promising new approach to solve those kinds of problems, and we hope that the release of our software will help build bridges between graphics and other scientific communities. Mitsuba works with Linux, macOS, and Windows in all recent Python versions. Installing it is as easy as running pip install Mitsuba on the command line. If you have an NVIDIA RTX graphics card, Mitsuba will use the built-in ray tracing hardware acceleration and nothing else needs to be installed. Alternatively, we also provide a CPU backend which requires you to install an extra dependency called LLVM. Follow the instructions shown here depending on your OS. Mitsuba consists of two main parts, a specialized compiler which is called Dr. JIT, and the renderer itself. The tutorial videos here will walk you through various examples of using both of these components, and we'll keep on adding further videos over time. Both are also documented on Read the Docs, where you can access tutorials, how-to guides, and reference documentation. We hope that you will find Mitsuba useful, and we're excited to see what you will do with it.